Today we are going to talk about graphing general rational functions, and this is the first video to start a trend, essentially, like start all these videos on all the different parts of a rational function. So just so we know, we are going to be learning about vertical asymptotes. Why is it? I'll actually type it because that's quicker. Vertical asymptotes, horizontal asymptotes, intercepts, so x and y intercepts, um, holes, and if time permits, oblique or slant asymptotes. So it's really important that we realize that there are a bunch of different parts of a rational function. And rational functions, when graphed, look really funky. So I'm telling you that as a fair warning now, that when you see the function, it might not look as pretty as other functions that we've done, right? So like when we've done quadratics, the parabola, it's a parabola. It's simple. It just goes, it sometimes gets skinnier, sometimes it gets wider, but it always looks the same. There is no general rule of thumb of what a rational function looks like. It looks like a hot mess every time, essentially. But before we get started, let's talk about the parent reciprocal function, which is 1 over x, which we did in the last phase. So first things first, we want to know what it looks like. So we remember it looks something like this and that. So the question is, oh, are there any vertical asymptotes? So let's review what an asymptote is, especially vertical. It is a line that is not necessarily part of the graph. It could be, for vertical, it's going to be a vertical line that the graph infinitely approaches but never touches. Okay? Horizontal asymptotes do differ in definition, but for vertical asymptotes, it will never touch it. And we're going to talk about why in a minute. But is there a vertical line that this function infinitely approaches but never touches? Well, it infinitely approaches the y-axis, which is a vertical line, right? Which is, what is this line? X equals 0. So my vertical asymptote here is x equals 0. So the question is, and let's actually look at this on Desmos, right? So this was our reciprocal function. You see how it's infinitely approaching that line. It will never ever touch it. See how it's infinitely getting closer and closer and closer to x equals 0. Like look at the x value, right? Look at that x value and how it's 1.22. It's going to get closer and closer and closer and closer to 0. But see, 0.91, I'm struggling here. 0.89, 0.88. It's getting closer to 0, but it is not going to ever be 0. Why is that? Why will the function never exist at x equals 0? Well, what have we learned about the domain of this function? So how do we find the domain of this function? Well, the domain is when the denominator equals 0. Well, the domain does not exist when the denominator equals 0. So I take my denominator, so for domain, I find what values make the function undefined. Well, all real numbers work for this, but x cannot equal 0 because if x equals 0, then the entire function is undefined. So therefore, there is a vertical asymptote at that value. So that is how we are going to be looking at vertical asymptotes. Vertical asymptotes, I would argue, besides the y-intercept, is the easiest portion of rational functions. So let's define a rational function in general first. So we have, let p of x and q of x be polynomials with no common factors. Okay, that is key here. You have to simplify it before you graph it. Before you simplify it, because In a later video, we're going to talk about removable discontinuities, which are also called holes. That it only exists when there are common factors, but you need to simplify it first. But what did we say we do before we simplify? Right? When we simplify, just a review of simplifying, when we simplified, we always found the domain first. Domain first, then simplify, and then technically, then graph. Okay, so no common factors. That is, again, key. So other than one, there's always going to be a common factor. One will always be a common factor between any two numbers or polynomials. So p of x and q of x, and it's going to be p of x over q of x. What has to be true with this? Q of x cannot equal 0, right? Because if the denominator is equal to 0, that's a problema. So this is general form. We've worked with general form when we spoke about polynomials, where we have a sub m x to the m power, a sub m minus 1 x to the m minus 1 power. So what is the degree of p of x? Well, the degree of p of x is m, and the degree of q of x is n. Okay, we aren't really going to work with that as much today, but for the next video, when we talk about horizontal asymptotes, the value of m and n are really important. Okay, so let's talk about vertical asymptotes. What's a vertical asymptote? In a fully simplified, I'm going to keep emphasizing this, fully simplified rational function, no common factors other than one. The values that make the function undefined, or the values that are not in the domain, are the vertical asymptotes. So that is why finding the domain is really key here. So let's do an example. So we have g of x equals 2x minus 8 and then x squared minus 9. Now the numerator is really unimportant when it comes to finding the domain. However, when we're talking about vertical asymptotes, again, we want to make sure it's fully simplified. So I would always recommend factoring both the top and the bottom in order to check, is it fully simplified? So I'm going to factor the top. The common factor between 2x and negative 8 is 2. So I'm going to have x minus 4. And then the denominator is a difference of perfect squares. So it's going to be x plus 3, x minus 3. Does it have any common factors? No. So I know it's fully simplified, so I can move on to finding my domain. So my domain is I set this not equal to 0, and so I get x cannot equal 3 and negative 3. So it's all real numbers, but x cannot equal 3 and x cannot equal negative 3. So on a graph, forget about everything else. Right now, we're just focusing on vertical asymptotes. What are my vertical asymptotes going to be? Well, that's pretty easy, considering we already found our domain and it's simplified. My vertical asymptotes are going to be, and I'm going to put it in this color. So my vertical asymptotes are x equals 3 and x equals negative 3. So I have x equals negative 3 here, and x equals positive 3. Now, what's important here is that means that this graph is going to have 3 separate sections to it. Something is gonna happen here, it's gonna happen here, something's gonna happen here. So depending on how many vertical asymptotes there are, right? If there's one vertical asymptote, then there's only gonna be 2 separate sections. If there are 4 vertical asymptotes, right? 1, 2, 3, 4, then there are going to be 1, 2, 3, 4, 5 separate sections of the graph. And I'm going to show you what that looks like on Desmos now. So if we look at Desmos here, this is the function we just graphed, right? And I already put the asymptotes in for us, 3 and negative 3. So look at this function. there is a section here, a portion here, and a portion here. You see how this graph is separated into three separate parts because these asymptotes are dividing it from being continuous. There is discontinuity from the asymptotes, so it is stopping it from being continuous. So it's really important for you to understand that those asymptotes are like walls. The function cannot cross the wall, so therefore, in order for the function to go from here to here, this has to be completely separate from this portion, and same for here. So let's look at another one. So again, the numerator is not valuable for finding the domain, but it is valuable for what? It's valuable to know if it is fully simplified. So I am still going to fully factor this. And we're going to be working with the same functions for the next few videos, so they'll already be factored for the next video. So it definitely will save time. So first thing first, what do you do when you're factoring? You want to take out the GCF. So 2x squared plus 3x plus 2, which then becomes what? 2x plus 2 and x plus 1. Again, I'm not going to review how to factor. Definitely go back and watch some videos on that. If you need videos on that, let me know. X plus what multiplies to negative 20 and adds to 8. So x plus 10 and x minus 2, which is fully factored. So are there any common factors? No, it is fully simplified. So we are good. And so what we have to do is find the domain. So I set this not equal to 0, and I get x cannot equal what? Negative 10 and 2. So my domain is all real numbers, but x cannot equal negative 10 and x cannot equal 2. So therefore my vertical asymptotes, because it is simplified already, is x equals negative 10 and x equals 2. So same concept. There are two vertical asymptotes, so therefore there are two sections of the graph. And so I am going to look at this. There are three sections of the graph. Here's the same function, and I put 2 and negative 10. And if you see, there are three sections, 1, 2, 3, where it's going, they're completely separate, but it's infinitely approaching our vertical asymptote. So look, everybody look at x. The x value is negative 10.3, whatever. It is going to infinitely get closer to negative 10, but it will never become negative 10. See how it's getting closer and closer? 3.31, 3.33. So all these things. Same concept. This is going to infinitely approach negative 10 from the other end. Negative 9.2, negative 9.3, negative 9.4. It's getting closer to negative 10. Here it's getting infinitely closer to what number? 2. So you are going to learn in pre-calc and calculus what limits are, and this is similar to limits where as x gets infinitely closer and closer and closer to a certain number, y gets infinitely closer to another number. Okay, and so last but not least, let's look at this function. So it's already factored for us because we don't know how to factor. We do technically. We've factored fifth degree functions using synthetic and long division, but I'm not going to put you through that right now. You're welcome. So what is the degree of the numerator? This is second, 2 x's, 3, 4, 5. This is a fifth degree function. This is 20 doesn't make a difference to our degree. That's just our leading coefficient. X, 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 so this is a third degree. Just remember that. That's a really important thing for us to remember, especially for the next video. Okay, so are there any common factors? No, we are green. It is fully simplified, right? So what I'm going to do is I'm going to find my domain. I'm going to set this not equal to 0. This 20 doesn't make a difference to my domain, right? 20 will never equal 0. So x cannot equal 6, negative 5, and negative 1. So my domain is all real numbers, X cannot equal 6, X cannot equal -5, and X cannot equal -1. Guess what? What are these values going to be? I put equals, cannot equal. These values are going to be my vertical asymptotes. Are going to be X equals 6, X equals -5, and X equals -1. And so, how many sections are going to be on this graph? So if we look at a graph, there's going to be -1, -5. Right, so let's say this is X equals -1, X equals -5, and X equals 6. How many different sections are there going to be? 1, 2, 3, 4 different sections of this graph. So let's look at it on Desmos. I told you it's going to start looking funky. Here it is. So I already put it 6, -5, and -1. Those are our asymptotes. But look, 1 section, 2 section, 3 section, 4 section. 4 different sections of this graph. So again, just really quick recap. If in a fully simplified rational function, the values that make the function undefined or the values that are not in the domain are our vertical asymptotes.